Okay, let's start. In the beginning of this class, I want to give a very quick overview over our homework platform, which is Archive Plus. Right? It's a shell that uses a proxy script to access archive papers, and a few of you have already been using it. Made me very happy. When you log into Archive Plus, you get this front page. This is the current status, and on the left side you can see the recent comments. So for example, Java left a comment on the paper, Patrick commented on the paper, and I actually replied to Shi Cheng's comment where I offered my opinion. So we can also have discussions of papers, not just single comments. And sometimes what I also do is I don't have time or have nothing really to add to the paper, but I like it, then I can like it, like on Facebook, or recommend, and then the website keeps track of recommendations, gives you the top recommended papers overall, right? So the entire user group voted sort of for the most interesting papers of the moment. Looks like Kitaya's paper received 2 recommendations, and at the moment with a small group of people, this is the top paper, but but that may be not so useful because you don't care what the entire community thinks is the best paper, but you are interested in your own subfield, right? In that case, we have thought about personal recommendations, and so this guy is a robot. He does it automatically. He just seeks out the keywords, like for me it's Majorana, and it offers me papers from the recent lists from yesterday, from last week, that have this keyword in the abstract or in the title. And so I can enter the keywords on the RSS page. You can click up there. And also, when I first did this, I got a lot of Majorana papers from astrophysics people and particle physics people. And I was saying, oh yeah, this is not really useful for me. So then I can also specify which archive lists, ConMat, quantum physics, those are the lists that I wanted to look at. So this is very useful for me. I just wake up, and with my morning coffee I get the papers that are relevant for me, and in the future you will be able to suggest papers to each other. Like you can send me a message, hey, take a look at this paper, and it will show up here.
Sergey, I have a comment about the comments field. It would be nice if you could track, or somehow it would notify you if someone responded to a comment you made.
Definitely. Yeah, that's a great feature to have. And then if you want to, this is for exploring what other people have done on Archive Plus. If you want to see what is happening on Archive itself, I like to use these links down here, which take me to the lists that I often visit, like the mesoscale and nanoscale physics. This is synonymous with quantum transport, right? So this is the topic of this course, and pretty much every paper will be relevant to what we discuss here. But here are some other examples, and you might be interested in other lists like material science lists. And if you're using something like a Google Reader or another RSS client, what I did is I replaced my archive RSS feeds with Archive Plus RSS feeds. So then here is a link where you can click, and then in your Google Plus nothing changes. You get the same abstracts from Archive, but when you click on them, it takes you to Archive Plus and lets you leave a comment, and also Archive Plus records that you have visited this paper. And it counts the statistics for the papers. So that is great. And so when we go into a meso list, it looks just like Archive, except we've added this field at the top, and we can pick a paper that sounds interesting. For example, this paper looks interesting, and if I find it nice, I can just click here and recommend this paper. Now the Archive Plus recorded that this is an interesting paper. You can also add it to my library for later reading. And I can leave a comment. Great paper. I don't want to leave a comment now because I haven't thought about this paper. And I don't want authors to freak out about some random text, even though this is just a game at the moment, they don't see it. But still. So please log in, please explore it. Remember, 1 comment per week. And this is the 3rd week. So let's say by Friday, we catch up with a count of comments. Even if you don't not registered for the class, I think this is a great experiment and a great game to play, because at the end of the semester we will prepare a report, and this report will be sent to the administrators of archive.org for their consideration of this experiment, and maybe they will embrace it for the big service. So we can make an impact on the entire science and on education. So please participate. Now we go back to quantum transport. And today's lecture will be very important. It will be a review of material platforms that people build devices out of to study quantum transport. And of course, you can do quantum transport in pieces of metal, right? As we discussed, if you cool a piece of metal low enough and maybe make it small enough such that an energy scale, such as a charging energy or a dephasing length, becomes larger than the size of the piece of metal, you will see quantum effects in pieces of metal, in tunnel junctions. Those are all very important examples. But actually, I don't have that much to say about them, other than you can do quantum transport with them. And we will have many examples throughout the course where quantum transport is done with, let's say, conventional Fermi liquid metal materials, or maybe tunnel junctions and things like that. But today's lecture will be dedicated to more intricate, more strange materials, such as semiconductors, molecules, self-assembled structures, and things like that. Because as it turns out, there is a huge variety of these materials, but there are many unifying features. And one of the unifying features is that you can make, in the clean room technology, you can make devices out of all of these. And you are making these devices every day. So let's start with these material systems, which are called two-dimensional electron gases, 2DEGs. This is not a random choice, because these materials are some of the most important materials in the field of quantum transport. They put the field on the map. Many breakthrough experiments were done using these structures. For example, the already mentioned here quantum Hall effect, fractional quantum Hall effect, many quantum dot experiments, and so you will run into these structures very often in this course and when you study quantum transport. And so what these structures are, well, I can also add that they came to us from industry. Industry was looking for high mobility structures with long mean-free paths to make better transistors. And then the physicists say, hey, you can do a lot of interesting physics with this, because these are ballistic and very quantum systems. And what they are is they are often so-called heterostructures. So they are material combinations where very precisely one semiconductor and put on top of the other, or as in the case of this structure, it is actually a semiconductor, silicon, and then on top of that you have an oxide, silicon oxide. And so needless to say, these are very high quality, pristine materials, and electrons live on the interface between two different materials. So in this case, they live on the interface of silicon and its oxide. And in this very important example, electrons live on the interface of gallium arsenide, which is a semiconductor, and aluminum gallium arsenide, which is actually an insulator. So here at the interface. Okay. There are several things to say here, because this is a very unusual situation. Nowhere in this material there is conduction, and only on one interface. And so when we start with a piece of bulk material, and on top of that we grow layer by layer with high quality another material, then at the interface you have conduction. Why is that? Because at the interfaces of different materials, various bands exhibit bending. Yeah, there are band offsets and band bending effects. And so, for example, in the case of gallium arsenide, aluminum gallium arsenide, what is drawn here is the bottom of the conduction band. So this is the bottom of the band. And this is the top of the valence band. So this thing will be the gap, yeah, the band gap of this gallium arsenide material, and this will be the band gap of aluminum gallium arsenide. Okay? But they are not flat. Near the interface, so far away from the interface they're flat, but near the interface they bend down, and then you go into a larger band gap, yeah, and then something else happens, and here you have the surface where maybe you put an electrode. So the Fermi level happens to lie right here. Okay? So in gallium arsenide, it's a semiconductor, so Fermi level is somewhere inside the band gap. But just at this point, at the interface, the conduction band dips down and goes below the Fermi level. Okay? And so you have this tiny, tiny region where electrons are allowed to live. And the dimension of this region can be 10 nanometers, 20 nanometers, and the density is very low. So the density of electrons in a typical two-dimensional electron gas can be something like 10 to the 11, 10 to the 12 of electrons per square centimeter. And if you work that out, then the Fermi wavelength, the size of the electron, so to say, will be also tens of nanometers. So it means that you can actually fit only one electron in this thickness. So only one electron can fit here. In that sense, these layers are called two-dimensional. Yeah? And it's a two-dimensional electron gas because in one dimension electrons are confined, but in this plane they're not confined. They are free to fly in 2 dimensions. Pretty much the same story you have over here with silicon and silicon oxide. There is a conduction band, a valence band, a Fermi level, and near the interface you have this dip, and electrons are allowed to live here. There are differences. For example, electrons in silicon are much heavier than electrons in gallium arsenide. So the geometry of this dip has to be very different to call it a two-dimensional electron gas. Now I also want to say why these structures are of such remarkable quality and why they're so useful. So the Y is the mean free path in, for example, gallium arsenide. Why is it reaching into tens of microns in the highest quality materials? Well, that is because the way they grow these structures is they make a perfect interface, and these two materials are very well matched, so the lattice constants are very close. Yeah? So there are no defects at this interface, there are no crystalline defects. And the reason why you have this dip and why you have these electrons here is because there are donor atoms, but those atoms are far away from the interface. They live here. They're silicon donors. They live some tens of nanometers away from the interface. And therefore, this layer of donors, they don't introduce disorder where electrons fly. So this idea of separating a donor layer So the layer from where electrons physically come into the two-dimensional electron gas. From the interface where the gas is formed, that was a great breakthrough that allowed to increase these mobilities and make many great devices. In this case, there are actually no donors. So in order to populate this little kink here, you must apply a gate voltage on the electrons. So electrons come from here, from the surface. And if you don't apply this gate voltage, there are no electrons here. So it's a completely empty structure, and you have to induce electrons from far away. That also results in high mobility. And for example, quantum Hall effect was actually discovered in this material, in silicon oxide, so-called MOSFET, metal oxide what does it stand for? Semiconductor. Metal oxide semiconductor. And FET is a field effect transistor. All right, we figured it out. But then, for example, a fractional quantum Hall effect, which requires even higher mobilities, was discovered in this structure. And this is a very famous graph from Loren Pfeiffer, who is one of the leading growers of gallium arsenide, aluminum gallium arsenide structures. And he has committed his entire career pretty much to perfecting the growth of these materials. And this is the story of his life, and now he has added a couple more curves up there. I have seen a newer version of this graph. I was just a bit lazy to dig it out. But here's what you start with in a bulk, so where you don't have that interface between gallium arsenide and aluminum gallium arsenide, and you have various defects. The mobility hovers around some thousands in the units of centimeters squared divided by volt times second. That's the unit of mobility. And if you want to figure out the conductivity from it, you have to know the density. And if you know the conductivity, you can figure out mobility if you know the density. So we will get back to these expressions. And as a reminder, mobility is this proportionality between drift velocity of particles and the electric field that you apply, right? So voltage. On this axis you have temperature. So mobility grows typically with temperature, except in the bulk for various reasons related to semiconductor physics we will not discuss. But in clean structures, in heterostructures, it grows because you freeze out various impurities. And it grows to higher and higher level, and I think by now he can make 30 million in his lab, which means a mean-free path of something like 50 microns. 50 microns is huge compared to, for example, the wavelength of an electron of 30 nanometers. Yeah? So that's a factor of 2,000 larger than the wavelength of the electron. And it is large compared to any transistor that you would ever want to make. Yeah, we actually want to make them smaller and smaller. So this is a remarkable achievement, and it allows them to discover new physics even now. For example, in the area of topological quantum computation and 5/2 states in these materials. So it's still worth improving it even more. That's the point. But this is what they can do with these materials. So these are very important materials, and for example, the textbook of Thomas In, the Semiconductor Nanostructures textbook, is dedicated to this material to a large fraction, and a textbook by Datta, I think, is almost 100% written about experiments done in these materials. And once again, this is how you would make using this material. And I like this picture because it gives you a three-dimensional perspective. So here is the interface, and so gallium arsenide, aluminum gallium arsenide, and at the interface, by this blue, we indicate a layer of two-dimensional electrons. This is typically about 100 nanometers below the surface of the crystal. And we have access mostly to the top of the crystal. So the first thing we need to do is to contact these electrons. So we deposit some metal on top, and then we heat it up in an oven. We anneal it, and this metal diffuses down and makes contact 100 nanometers below the surface. Yeah. And then we want to define, for example, these little puddles. They're quantum dots. And so the structure that we made here is a quantum dot, so a double quantum dot with some contacts. And on top here, we have a narrow point contact and another point contact. So we have two quantum dots and 2 point contacts and some leads. The way we do that is by electrostatics. So on the surface, we have these metals, and we can apply voltages to these metals, which changes locally the density underneath in the two-dimensional electron gas. Like in a capacitor, you induce an image charge here, it will induce an opposite charge below. So these are electrostatic gates. I already brought gates up before, and I will use them many more times. So we have to be on the same page about gates. So for example, if I want to get rid of electrons underneath this gate, so the orange color means zero density, no electrodes. What kind of voltage do I have to apply? Everyone agrees? What is the sign of voltage?
Should be negative.
Negative, right. Exactly. So the electrons have a positive charge. It's like a capacitor. So if I induce a negative charge here, it will induce a positive charge here. The electrons have a negative charge, so it will cancel the charge of electrons. And I have to apply, to completely get rid of electrons, I have to apply the charge that is opposite for the right density. Right? So if there are more electrons underneath, I have to go to higher voltages. Okay. So you can, this is how you can make nanostructures from the top. Okay. Now we move on to other materials. This was a two-dimensional system, right? Two-dimensional gas of electrons. This is an example of a one-dimensional structure. So there's nothing other than this wire. These wires, they grow like this. I'll have a separate lecture a bit on technology of how these materials are produced. This one is not carved out of any piece of metal. It is really one-dimensional. And the diameter of this wire is, again, tens of nanometers, so about the size of an electron in a semiconductor. Right? And these are still semiconducting materials. These can be gallium arsenide, this can be gallium phosphide, indium arsenide, a whole variety. It could be silicon. So electrons cannot leave the wire, and only one electron fits in this wire. So effectively, it becomes a one-dimensional system that can conduct electrons. In this case, of course, we cannot do remote doping from a donor layer, like in a 2DEG. We have to dope in the same space as where the electrons live in order to induce conduction in this semiconductor. So as a general rule, you cannot reach such high mobilities in these one-dimensional structures, but you can go to tens of thousands. For the 2DEG, we were able to go to tens of millions. Here we can go to tens of thousands. Factor of 1,000 worse, but still useful for many interesting experiments. And you can also produce heterostructures. Like in this example, the two different colors are two different semiconductors. And so by changing various gases in the reactor, you can switch from gallium phosphide to gallium arsenide. And depending on how long you grow with arsenic precursor or a phosphine precursor, you will get different length segments of different semiconductors.
So it's not possible to grow a gallium arsenide wire and then have this lateral growth of gas with the remote dopant and stuff.
Yeah, that is also possible. Yeah.
And then you have a helical tube.
Yeah, you can imagine a TwoDiag, which is a tube.
Right. So this is possible.
Yeah, it is possible. That is possible. But it will no longer really be a nanowire because you have to grow several layers laterally and then a separate layer for dopants. But indeed, this is a good example. Okay, but this is not the only way to get one-dimensional wires, so one-dimensional conductors. For example, here, this group have started with a 2D structure and they etched out a wire. They used some chemical etchant and out of a two-dimensional electron gas, they've etched, so the bright shades here are where you still have electrons, and in between there is nothing. It's just etched down. And so as a result, they got a one-dimensional wire with some contacts. And in general, the two approaches have names. This one is called top-down, because they start with something two-dimensional and they etch it down to one-dimensional. And this one is called bottom-up, and they grow a one-dimensional structure. And finally, we can also have objects which are zero-dimensional, the quantum dots that already came up a few times. And this quantum dot I just discussed when I explained to you in 3D how you can make structures out of 2Ds. And so this is now a top view on a gallium arsenide, aluminum gallium arsenide heterostructure, and this gate pattern above. By applying voltages to these gates, we can create a quantum dot here, a quantum dot here, and a quantum wire here. So we can create a one-dimensional channel and zero-dimensional channel. And this is an example where we etch down from a larger area, and we etch down a perfect circular shape to create a quantum dot, confine electrons to a pillar. Again, the size of this pillar is about the size of an electron, so you cannot fit too many. But this was a very nice experiment done about 15 years ago, where then by using a gate, they could add electrons to this dot. And they could change the number of electrons from 0 to 1 to 2 to 3, etc., one by one. And they could create their own sort of periodic table of artificial atoms. And because they had a perfect shape for these dots, the orbitals of electrons in this dot had perfect symmetry. So they could really map it to s,p,d orbitals like in atoms. And they even made a bit self-indulgent periodic table where these letters stand for the people involved. For example, I know some of the abbreviations I could guess them for. This would be Seigo Tarucha from Japan, and this would be my boss Leo Kauenhoven, and this is probably Ono. I don't know all of them. You have to look at the original papers, but in the case of a perfect shape, it really made sense for them to think about orbitals which are degenerate and make this artificial atom periodic table. It's not so easy to do that in this case because these dots don't have such a perfect shape. They are defined by several different electrodes, and these orbital symmetries do not hold in that case. Well, this is yet another way to get a semiconducting quantum dot. We are still in the realm of semiconductors here, by a so-called self-assembly. So in this case, they start with a semiconducting substrate, and they try to throw down atoms of a different semiconductor, which has a huge mismatch with the original semiconductor. They're very different semiconductors. So this is the opposite approach to this, where they try to put gallium arsenide and then aluminum gallium arsenide go on each other like perfect layers. Here, because there's an enormous strain between these two, for example, indium arsenide dots on, maybe it's gallium arsenide even. This indium arsenide, the white specks, they, to minimize strain, they cluster together and they form little pyramids which are about 100 nanometers in dimension. So again, about the size of an electron. So you can put only a few electrons here. And if you wanted to make a device out of this, you could come in and put a couple of electrodes on this little bump. And you can even add a gate from the side. So you can again have a device, and you have a template, so a bottom-up produced quantum dot, which is a semiconducting quantum dot with a few electrons. So this would be a bottom-up approach. That would be a top-down approach. I want to make a side comment that these are also very convenient structures for optical studies, because rather than going through the hassle of contacting them with various electrodes, you can just shine a laser on them and then interrogate their quantum properties, their spectra, etc. But since we are in a quantum transport course, I don't discuss optical experiments much, though they are quite related. Okay. Now the previous examples were all similar in the sense that we were either growing 2D layers or 1D layers or even little bumps of self-assembled dots, but those were all still fairly big. They were about the size of an electron, but if you count the atoms, each of these objects had millions or billions of atoms. And in that case, we can talk about a well-defined structure of bands, band structure in a semiconductor, which is the same as in a bulk semiconductor. We don't even have to make any modifications. And if you have 1 million atoms, you can just use the bands that you derived from the bulk semiconductor and apply it to the nanoscale object. And so we will discuss band structure very quickly as a next item. But before we go there, I wanted to show you these examples where we only have a few atoms. These are grown by chemists by sort of synthesis techniques and in the wet methods in these kind of vessels. These are still semiconducting atoms. These could be, for example, cadmium selenide objects or other objects which are so small that there are only a few atoms. And to know the electronic spectrum, the bands in these materials, you pretty much have to do a separate calculation taking into account maybe all of these atoms, how they are arranged. So this is an object which is a transition between the bulk, maybe nanoscale but still bulk, and the world of molecules and atoms. So there's something in between. These are very famous compounds. These pictures are firmly associated with the words quantum dots. Actually more than what I showed you before, more than these quantum dots. People think about quantum dots when they look at these capsules. And who can tell me why they have different colors?
The size.
That's right. They have different size. So they absorb and they emit a different wavelength based on their size. So the chemist can synthesize a perfect array of different sizes. And again, you could also even do quantum transport with these. You could imagine dispersing these little capsules on a surface and then finding them, contacting them, etc., etc. And finally, we go into single molecules. We can also do that in quantum transport. There are experiments where, for example, people studied current passing through single DNA molecules. It turns out that the DNA is a perfect metal, among other things. Not very useful property, but anyways. At some point, there was a joke that DNA stands for direct nature access, because anything you measure on DNA goes there. Okay, so this is worth spending a few moments on, because this is really the ultimate limit of quantum transport. And so what we are doing here is we are trying to pass a current through a single molecule. And for that, you need some special machinery. It's not so easy. What they have developed is these are various techniques where they created two metal electrodes with a tiny gap in between them. And then they throw molecules randomly, and sometimes molecules land in between these gaps, and then they measure a little current going between. That's the method. And then there are different ways to create these gaps. You can, for example, create a not so small gap and then bend the chip until the gap opens like a bridge. Okay, so this is already a constriction, and then you push and it bends, and the two sides of the bridge come apart until there is maybe only one atom remaining, and then finally it's open. You can burn a constriction. You can start with a wire which becomes narrow and send a huge current through, and that will actually burn the wire. That's called electromigration technique. So there are different ways, and then there are different ways of putting down a molecule in that bridge. For example, here they have attached a molecule to huge gold spheres, and then it's like two balls on a chain, and when the two balls land on the opposite electrodes, you can measure a little current going in between. Sometimes they create molecules like that, where here's a molecule, but it has two synthesized arms. So chemists can do anything, and sometimes they can just synthesize two arms for a molecule, and these molecules will prefer to grab onto the two electrodes and make a bridge. And the holy grail in this field of molecular electronics is to relate the properties of the molecules, so the electronic spectrum of the molecule, to the conduction properties, so the quantum transport properties of this final device. And then it turns out to be quite a challenge, but they have some success. The biggest problem in this field is that every device that you make is different. Even the fact that the contact can have several different configurations, different number of atoms, completely changes the properties of current that you pass through. So for example, here's an experiment where they've done 12,000 curves, and they measure conductance, various instances, and they plot it. You have to plot it as a histogram. And this is very interesting data because, for example, you can see several peaks in this histogram that correspond to values of quantized conductance. 1, 2, 3, 4, maybe even 4 of 2e²/h. Of course, you have all values in between as well, but there are some peaks. So from 12,000 devices, 12,000 times you try this experiment, you can make some conclusion. And the conclusion is that basically when you are around here, you have just one atom connecting the two electrodes. And the conduction through that one atom is like conduction through one quantum channel, and that is about 2e²/h. And when you're around here, you have two atoms, and you see it getting much less perfect already. This is maybe with two atoms, transmission is not 100%, and so you get a little shift here. And here you are with three atoms, etc., etc. So from statistics on single molecules, they were able to conclude something, but from a single device, it is very difficult. And these are also very fragile. This one molecule can fly away, get burned. So the field was very exciting, and then it became rather frustrating. So I don't think in this course we will talk much about this, but I just wanted to show that people went there and they tried it very hard. And it's great. And now we discussed semiconductors that can be 2D, 1D, 0D, obviously 3D. This very important element, carbon, can exist, as many of you know, in all shapes, from 2D to 0D, and of course in your pencil it's 3D graphite, and in your diamond ring it's also 3D. So this is a beautiful set of materials for quantum transport. Especially graphene and carbon nanotubes gave rise to many interesting experiments. And since this one material can exist in all these shapes and forms, I thought that we would spend a little bit of time very quickly reviewing the difference between 2D electrons, 1D electrons, 0D electrons, because there are some subtle differences which you may or may not remember from your solid state physics course. We will go very quickly through these formulas, but the starting point of this discussion is electrons just in 3 dimensions, right? And the quantity that I want to derive here is the density of states, because that is the difference. In 3 dimensions, electrons obey Schrodinger equations, and the solutions are plane waves, and the energy eigenstates are the energies of the plane waves, right? The kinetic energies. You all know that very well, but if I ask how many states, quantum states, are available in a particular volume, volume and K space, right? That's what I'm interested in. Then I just have to calculate the volume, and the function will be like that. So this is how many states there are in a unitary volume in K space. And there is a degeneracy factor of 2. Okay, if I want to express it in terms of decay, so for go from a vector notation to just if I increment by k by a small amount, then I have to integrate over a sphere. And so k can point in any direction in 3D, and then dk vector becomes 4 pi k squared dk, like that, and that means that the density of states has a dimension of k squared. And k squared is related to energy. So at the end of the day, these calculations are basically simply from Ashcroft and Mermin or any solid state book, Kittel. You get that the density of states in 3D is for a given energy now proportional to the square root of energy. Is this familiar to everyone, most of you? Yeah. This should be well known to you, and the density of states is you know, remember that it enters into all kinds of calculations. For example, what is the Fermi energy? You have to know the density of states. Basically, how many electrons can you fit up to a certain energy? That's where density of states is important. So it's a square root E in 3D. It's a graph like that. So the density of states grows as you increase the energy. And who remembers what happens in 2D?
Wow.
Exactly. So again, I can go through the derivation. It's the same derivation. Energy is now has 2 components here, and the decay is this, 2 pi k decay, right? So we have to integrate over a circle, not a sphere. And then in terms of, if we convert it to energy, we have a square root energy here, but we have inverse square root here, and we have a square root here. And they cancel, and the density of states is flat in 2D. So in 2D, it doesn't matter where your Fermi level is, the density of states is always the same. Now in 1D, what happens?
1 over.
Right. So there's an anomaly. So in 1D, dk is equal to dk. There is no surface anymore, and so there's nothing to cancel this inverse square root, so it remains. And so the density of states in 1D actually drops as you increase the energy. And the near zero energy has an anomaly. It's called Van Hove singularity. Yeah? So we all know this, right? Now let's go from free electrons into a material, right? In a semiconductor or metal. We have to again solve a Schrödinger equation, but we now have this periodic potential of atoms in a crystal lattice, right? And we all must remember that the solutions in this case are not free waves but Bloch waves. They look like free waves, but they have a prefactor, which is this term coming from the potential. So it's a function which is periodic in a crystal lattice spacing, etc. So this is called the Bloch theorem, right? We all remember this. And the solutions, the energy solutions for this equation also look very similar, except this mass doesn't have to be the mass of a free electron, it can even be energy dependent. So this is on a very general level. And in general, you can have in a metal, or especially in a semiconductor, you can have a number of different bands which you can calculate by considering the crystal structure and figuring out the exact structure of these U of k functions, the Bloch functions. And so then the way you can see that there are different effective masses is that these parabolas will have different openings. Now there are different approximate methods for calculating band structures for important materials, which take into account the crystal symmetry of the materials. You can read about it in a textbook if you need a reminder. I was actually assured when I started working on quantum transport that I don't have to know the physics of semiconductors. And I can, in principle, assure you of the same, but it's good to have a small overview. So for example, by doing this pseudo-potential method, it's called, where we approximate the potentials in a crystal lattice by inferring actually from experiment the empirical parameters like band gap and various ionization energies, and feed them back into the Bloch equation to get the right gaps in the spectrum. Then we can get these kind of bands. For example, for silicon, there are certain peculiarities because the fundamental band gap is the distance from the bottom of the conduction band to the top of the valence band, and you can see that the two don't coincide. They are for different values, for different directions in the inverse space, in the momentum space. So this is an indirect band gap material. It also has different valleys and complicated band structure. This band structure you see very often when you work with 3-5 semiconductors, such as silicon, such as gallium arsenide, indium arsenide, etc. There you typically have, just ignore the dashed line, you just have a single conduction band. That's very simple. And we can think about a free electron gas, like a two-dimensional electron gas, with one particular mass, one particular G factor, and that is why you don't have to know the physics of semiconductors if you only think about electrons in this conduction band. Now at the valence band, it has quite a bit of structure. There are 3 bands. There's one band which is split off, and this splitting comes from spin-orbit interaction. We will discuss it later. And there are 2 bands. One is called the heavy hole band, and one is called the light hole band. So why the names? Who can tell me?
Effective mass.
Right. So which one is the heavy hole band, and which one is the light hole band?
Truly heavy.
Right. So the more open one means the mass is larger. Right? This is the heavy hole band, and this is the light hole band. They also have different interesting spin properties. And so And if you were in silicon, you would have this other band at a different K value hanging down here. Okay, so this is again the silicon main structure. I already pointed it out. And this is the gallium arsenide. So again, you have two whole bands, another one split off, and a fairly simple conduction band if you don't go too far. If you stay down here. Now, the carbon systems are rather different. The band structure is somewhat different, and a particular method used to calculate this is called a tight binding method. And the way that works is, rather than assuming some fairly generic pseudopotentials in the crystals and then backfitting the parameters of these potentials, so kind of glossing over all the details of the atomic structure, here more of the atomic structure of the material is brought into play. What the people do here is they say, okay, each one of these carbon atoms, or these carbon atoms, has 4 electrons available. And it has 4 orbitals on which these electrons live. And one is pointing kind of out in the z direction, out like that, and 3 are pointing in the plane. So here, here, and here. So those 3 are used to couple to the neighboring atoms. And 1 is left to conduct. So then the orbits in the plane are undergoing this sp2 hybridization between s and p orbitals, and the pz orbital remains sticking out like that. So those are the electronic clouds that we have here. And then what people do is they say, okay, let's add up all these orbitals in a hexagonal lattice and consider the 3 electrons tightly bound inside a single atom, and 1 is allowed to hop. So they construct the band structure from these orbitals. That's called the tight binding approximation. And I don't have time or desire to go through the entire math, but it can be found in, for example, in the book of Thomas Inn. But the result of this calculation is that the band structure looks like this. Very interesting, because here is a top view of this Brillouin zone. So this is an inverse space, and these are the K points. There are 2 K and K prime because there are 2 electrons per unit cell. So there is a so-called valley degeneracy. And in the middle you have this M point. So at the M point, it turns out there is a huge gap. Well, fairly huge gap between the kind of the pi star and the pi band, which you can think of as a conduction band and a valence band. But at the K points, this gap is 0. The 2 come together, and so you have this hexagonal symmetry in this band structure. It turns out that if you leave this sheet of graphene alone, the Fermi level will exactly be in this symmetry point, because you have 2 electrons per unit cell and you have 2 spin components. So this band will be fully filled, and this will be completely empty. This will be the Fermi level. So this will be the symmetry point, and because near this point the dispersion relation, this momentum energy dependence, is linear. People talk about the Dirac spectrum of relativistic electrons in graphene. So this is, I guess my point is that this band structure is rather different from this one for semiconductors. Now another important point I wanted to make is this difference between bands and subbands. So if you are in a piece of semiconductor, of course you have to obey the band relation. You have to be if you want to be a free electron, maybe you want to be in a conduction band, or depending on where the Fermi level is. And there are certain gaps in the band where you're not allowed to be. There are no states there. But on top of that, you can further confine your structure. So for example, like is shown here, this is a piece of semiconductor, but then there are two walls in that semiconductor. And in that case, you can solve a Schrodinger equation for block waves. So then those free waves will become confined, and there will be a discrete spectrum on top of the band structure. So then the block waves, we think of them now as free waves, and those free waves can be further confined. And then there will be a discrete spectrum of allowed energies in this case, at least associated with motion in this dimension. Like a particle in a box, there will be a spectrum, but in this dimension, for example, they will be free to move in a crystal. So in this dimension, there will be just free block waves. So this situation, in this situation, we call these structure, these subbands, living in a band structure of a semiconductor. I think that's an important distinction to make maybe once. So this will be an example for one-dimensional structure. We may have a piece of two-dimensional electron gas, or even a bulk semiconductor, confined in 2 dimensions, so only 1 dimension is left free. But that confinement introduces a discrete spectrum of eigenstates, and each of these eigenstates is like a subband in a band, in a conduction band. And each of the subbands will have this density of states of a 1D structure. So you will add them up like that. Each will have a Van Hove singularity. Here's an example for 2D. This is maybe a 3D material which is confined in one of the dimensions, so 2 dimensions are free to go. And you have this discrete spectrum associated with the confined direction. And but in the other 2 dimensions, in x and y, for example, you are free to move. So in those dimensions, you have a parabola. And so from each discrete point, you will have a parabola dispersing. And if you ask yourself what is the density of states, it will be this kind of a staircase. So this is making the same point. This is now confinement in 1 dimension, and the 2 dimensions are free. For each of the eigenstates, you have a parabola, and the density of states is a staircase. And this one summarizes all the way going from 3D to 0D. And in 3D, we don't really have subbands because we are completely free to move. And so we just have this density of states going as square root of E. In 2D, we can have subbands associated with a Z, with a confined direction, and we will have the red staircase, where these points are the energies of the higher and higher subbands. In 1D, then we will have subbands, and each subband edge will introduce this singularity. And then in 0D, we just have single quantum levels, like a particle in a box solution. And so they will have only occupancy at the single quantum levels and nothing in between. So the black dashed lines are the 0D case. Okay, so now this is a tricky one. Remember this material? We started with it, 2-dimensional electron gas. So now the question is, this is not a bulk material, or maybe it is a bulk material. It's an interface. But are these electrons forming a band or a subband? What do we say?
Subband.
Subband. Any other opinions? No one cares? Everyone agrees? Shall we vote? Let's vote. Who thinks this is these electrons form subbands? Who thinks they form bands? 3 people. Okay. So subbands win. I think these form subbands, indeed, because okay, they live on the interface between 2 different materials, both, and so if you want to know the exact properties of these electrons on the band level, you have to kind of integrate over the band properties of aluminum gallium arsenide and gallium arsenide. But still, they are confined in one of the directions. Externally by these potentials, but still they are confined. And actually you can have multiple subbands in this well. If you put more dopants here, you can get into a situation where electrons don't fit in the lowest subband and you have to go to a higher energy level. So for example, associated with this a very sharp dip could be an energy scale of tens of milli-electron volts. So the electrons will live down here, and then 10 millivolts higher, there will be another band of electrons. So for example, if you go to an electron density of few times 10 to the 12 centimeters minus in the minus second power, you will most likely hit the second subband in gallium arsenide. So there will be 2 different subspecies of electrons living on top of each other with different energies. So those are very interesting experiments. So I think in this case these electrons form subbands. But that actually was an easy one. This is a hard one. I don't actually know the answer, but this is a carbon nanotube. I don't know how many of you are familiar with these objects, but carbon nanotube is a piece of graphene that has been rolled up and connected into a tube. And the first thing that anyone realizes is there are many different ways to do that. And you can take a piece of graphene and roll it like that, or you can roll it like that, or you can take these 2 atoms and connect them. So you can basically take one atom and connect it on the other side of the sheet to any different atom, and that will form a tube. And that will form sort of a different boundary condition to calculate the electronic structure in a nanotube. There is a whole table of different chirality vectors in x and y of the graphene sheet for depending on which points are the same in a tube. You have different electronic properties. These are the most famous examples are zigzag armchair nanotubes. Yeah, so you can see that there is a small difference between them, between how the atoms are arranged. And this one is kind of arbitrary. So you can see these lines sliding down. That's the chirality of the nanotube. So I'm a bit torn here whether to call what electrons form here bands or subbands, because in principle it's a piece of graphene confined. Yeah, you just cut different shape out of a piece of graphene, but at the same time the properties can be so different. Sometimes there is no gap, that's called metallic nanotubes. Sometimes there is a gap, and they're called semiconducting nanotubes, and it really, or insulating nanotubes, and it really asks for to be called bands. So I think officially they're called bands in this case. And so this is it's a very nice exercise to calculate band structures of different nanotubes. By now there are even little apps online that you can play with chirality and get the electronic spectrum. But the general approach is very simple. It goes like this. You have this band structure for graphene, and it's replotted here, looking from a different angle. This is the first brilliant zone, and these cones where the pi and the pi star bands come together. So these Dirac cones, and these are filled and these are empty. And depending on how you roll the nanotube, what you're doing in this band structure is you're drawing these dashed lines. And those are the lines of where electrons are allowed to live by the boundary conditions. And you can draw these lines any way you like. You can draw it going through for these points. You can draw it at any different angle. You have to draw this parallel set of lines, and this is how you discretize a two-dimensional band structure into one-dimensional band structure. And you can already see that, for example, if this cuts somewhere in between these cones, there will be no conduction. This will be an insulating nanotube. And if it cuts right through the cone, like is shown here, you will have perfect conduction. In fact, there will be no gap in between the valence band and the conduction band. So this will be a metallic nanotube. And if you cut very close to the cone, but not quite through the symmetry point, through the Dirac point, you will have a gap, but it will be a small gap. So that is called a semiconducting nanotube. Right? Depending on how you roll the tube, you can have anything you like.
There are two types of band structures, right? So very similar to the topological. It's different, right? I mean, the band structure.
Yes, topological also have a Dirac cone. But these are not topological because there is an even number of these cones.
Okay.
Okay, and actually you can have subbands on top of these bands. So you can start with a metallic nanotube, Dirac cone, but it can have also a higher energy state. When you fill up to the next energy level in a nanotube, defined by the confinement of the tube, you will hit the next subband, and it will introduce an anomaly in the density of states. So this is a kind of a band-subband blurred zone, a nanotube. So in the case of nanotube, we have to be careful. But for example, in the case of a semiconducting nanowire with a diameter of tens of nanometers, we can just assume a band structure from that semiconductor, gallium arsenide, for example. And on top of that, we have to calculate confinement that will give us the subbands in a nanowire. Okay. And you can actually go and measure this density of states with a STM technique. This was done a few years ago. You can see different nanotubes with different chiralities, and this is the calculated density of states from higher subbands and the band gap, and this is the data. So they go in with a scanning tunneling microscope tip, apply different voltages, and depending on how easy for electrons to tunnel from the tip to the nanotube, they get a higher signal, a higher current. So there is a decent match, and they can also, they think they can even map out chiral zigzag or armchair nanotubes. There might be better data since this is one of the first experiments. That's why I show it, but it's already fairly old. Okay, in a few remaining minutes, I want to flash a few of the materials that are more recent additions to the quantum transport family. And these are not semiconductors like what I spent most of the lecture on. These are not metals. They're not these carbon semi-metal structures. They're new. But in some ways they're similar. For example, this one has been very popular for the last few years. It is a whole family of materials. One of the most famous representatives is bismuth 2-selenium-3, bismuth diselenide. And this one is a so-called topological insulator. So the interesting thing about this material is that the bulk of it is insulating and the surface is conducting, and the surface has interesting transport properties related to the word topological. This material has atomic structure which has one unit cell has 5 different layers, so it's much more complicated. But actually, the sets of 5 layers are not so strongly connected to each other. So you can take a bulk crystal and you can break it, and it will most likely break at this line. Or you can even grow small flakes or wires of this material. So you can do top-down or bottom-up approaches to producing these materials. In this example, they have grown something that looks like a nanoflake or nanowires with a chemical method, and they have fabricated devices from this structure by putting contacts on these filaments and observing some quantum oscillations. So this is an example of a quantum transport experiment that was done with this material. This experiment is from, I'm sorry I didn't put the reference, but this is from a Stanford group. There are also a series of nice experiments from Beijing group where our class member Jun did his PhD. Those are very interesting experiments. So this is one new material. Here is another one that we, actually a few of us discussed this week on Archive Plus. So I invite you to join this discussion. We are also thinking of working with this material at Pitt, and they are already working on it at CMU. So this is molybdenum disulfide, and it is also a material similar to graphene in a sense that it can be produced in single atomic layers of this kind of structure. So layers like that. So molybdenum and sulfur atoms are arranged like that, and you can lay these flakes flat on the surfaces, make contacts to them, put gates on top of them, so you can make the devices. And these materials are also moving in a quantum direction. Recently, superconductivity was observed in these materials, for example. That was just this week on Archive, so this is happening right now. This material is moving into quantum realm right now. By the way, who can tell me what is fundamentally flawed with this picture? I'm always bothered by this picture. This was on the cover of the journal. This is, by the way, from Lausanne, this experiment.
You should see the atoms in the arrow.
Yeah, I'm really surprised that you can see these big atoms in the molybdenum disulfide, but the gold electrodes apparently have much smaller atoms. Okay, this is an artist impression. And the last 2 minutes, this material is familiar to many of you. This is lanthanum aluminum oxide, strontium titanium oxide. So it's an interface, a heterostructure, like we discussed in the beginning, with gallium arsenide and aluminum gallium arsenide. But now these materials are both oxides, and at the interface, again, you can have a layer of conducting electrons. There are experiments where people have made devices with these materials, actually at Pitt, in the group of Jeremy Levy. And these devices already show some quantum properties. For example, single electron transport, electrons going through a small structure one by one. Or I pulled this from an archive yesterday. This is a paper where they made a nanowire from this material by writing it with an AFM, and they've measured some superconductivity in this nanowire. Yeah? So they have created a one-dimensional structure, and they've observed some quantum effects with it. And I think there are many more quantum things that you could measure with this material, so we should all stay tuned for results from the Levy group on this material. So this material is something that is making a debut premiere in the field of quantum transport before our eyes. So with those 3 examples, I finished the materials lecture, and we meet next week for continuation of the course. Thank you.